Hello, sir, ma'am. My name is Darshil Singh Garewal. For the partial fulfillment for award of degree in Bachelor's Engineering in Electronics and Communication branch at Thapar Institute of Engineering and Technology, I have undertaken research-based capstone project under the supervision and kind guidance of Dr. Amanpreet Kaur. My research-based project is entitled as Designing Ear EEG Filtering Technique using FIR windowing and wavelet decomposition.
The main objective of this project is to study physiological artifacts in ear EEG. Brain waves were first recorded by Hans Berger in 1926 using two-coil galvanometers. Since then, due to numerous technological advancements, we now use various EEG caps and electrodes to measure and record EEG signal. The figure shown on the screen shows the measuring and recording of scalp EEG. This method requires a lot of expertise to measure EEG and is not fit for mobile data acquisition as placing numerous electrodes on scalp is not socially acceptable. Hence, researchers came up with a concept of ear EEG where electrodes are placed inside the ear canal to measure EEG signals. The figure depicted on shown on the screen shows how ear EEG signals are acquired. The dataset used contains both scalp and ear EEG recordings. First, the correlation between the ear EEG and scalp electrodes were calculated. The ear electrode placed in the left ear canal were strongly correlated with T9 and FT9 electrodes, as it is evident from the Excel sheet shown on the screen. All of these are the Pearson's correlation coefficients, and the average of Pearson's correlation coefficient is mentioned over here for the left electrode. Similarly, for right canal electrodes, they were strongly correlated with T10 and FT10 electrodes. And these electrodes are scalp electrodes, which are also shown in this figure. Here it is a T9 electrode, FT9 electrode. Although it's a 2D plot, it can be imagined as an electrode which is very close to ear, T10 electrode and FT10 electrode. Since it is already shown that some scalp EEG electrodes strongly correlate with ear EEG electrodes, therefore we can apply techniques which are used to remove artifacts from scalp EEG on ear EEG as well. But first we need to study the physiological artifacts present in ear EEG. ICA and IC label plugin are used to depict this physiological artifact present in the dataset. A high-pass filter has already been applied to remove artifacts caused by sweating, and average rereferencing is already done to make the potentials independent of the location of the reference electrode. ICA has already been applied. ICA's SOBI has been applied to the dataset, as it can be shown from the figure that the line noise is present at 50 Hz, and most of the independent components are contaminated by line noise. And in conjunction to line noise, also another peak at 100 Hz, centered around 100 Hz, is present. This peak at 100 Hz is due to EMG artifacts because the literature suggests that near temporal regions where the ear electrodes are present, EMG artifacts cause peaks between 45 to 120 Hz. Therefore, to remove these artifacts, we then apply three band reject filters centered around 50 Hz in cascade with a low pass filter with a cutoff frequency 80 Hz with keeping the bandwidth of EEG signal in mind. Filters used to filter out artifacts such as EMG artifacts and line noise are FIR filters. FIR filters are used because the phase response of FIR filters is linear in passband, and the first FIR filter to remove out sweating artifacts is high pass filter, and its characteristics are shown on the screen. Next, FIR filter is a low pass FIR filter with a cutoff frequency 80 Hz, which is used to remove EMG artifacts, is shown. Following this, three band reject filters whose characteristics are shown on the screen are used to eliminate the line noise. First band reject filter is centered around 50 Hz with a stop band from 47 to 53 Hz. Second has a stop band from 48 to 52 Hz, again centered around at 50 Hz. Third band pass filter is centered around 50 Hz with a stop band from 49 to 51 Hz. After applying these filters, it is observed that the peaks are no longer there and PST curves is close to 1 by F shape, which marks clean EEG. But EOG artifacts were still present. Hence, exploiting high amplitude and low frequency property of EOG artifacts, we then apply wavelet decomposition with dB1 as mother wavelet and rejecting output of low pass filter of quadrature mirror filters which was used to apply wavelet decomposition, we get clean EEG in which we have removed EOG, EMG and line noise. However, it is important to mention that no QRS complexes were present in the time series EEG data. Hence, we can conclude that no ECG contamination was there. The figure shown on the screen shows that how the data is filtered out from EOG signals. The data present between 2 to 13 seconds shows this. There was a peak, high amplitude peak at this timestamp, and using wavelet decomposition, it has now been decomposed to a high frequency signal only. After extracting out the artifacts, clean EEG was obtained. Then epoch extraction was done 1 second prior and 1 second after the motor imagery tasks present in the dataset. Newton pattern recognition network was then applied to clean EEG epochs to classify it. This sums up with the whole project. Thank you.